Okay guys, so here we go with the last lesson of chapter 5. So this is 5.6 part 2, which is applications of trigonometric modeling. So what we're going to do is look at if you were to model some sort of scenario using a trig function, how you would come up with the equation and then how you would use that equation. So one of the most common types of applications is a Ferris wheel question. And the reason a Ferris wheel question is common is because if you look at what a Ferris wheel does, you've got a person going around and around on a Ferris wheel, which is like your circle, which is how you graph a trig function. So what we're going to be looking at is we're going to be looking at specific scenarios of different Ferris wheels. So the first one is going to talk about a Ferris wheel that has a diameter of 30 meters with the center 18 meters above the ground, making one complete rotation every 60 seconds. And from that, we're going to try to come up with a trig function. Now, usually what you're going to do is you're going to come up with a cosine function, but we'll talk about why as we go along. But what we're going to do first is we're going to try to draw a graph of this scenario because it's going to help you understand what's going on. So first thing I'm going to do is draw exactly what I did kind of before, which is a circle diagram. So I'm going to draw the ground, and I'm going to look at the fact that you have a Ferris wheel of 30-meter diameter with the center 18 meters above the ground. So this is going to be the center of your Ferris wheel, which is going to be 18 meters off the ground. Then you're going to have a Ferris wheel with a diameter of 30 meters. So if the diameter is 30 meters, that means that the radius is 15 meters. So if you think about going from the center down 15, that's going to be your Ferris wheel. So this is going to be 15 meters from the center. So you're going to have the Ferris wheel being 3 meters from the bottom because it's 18 meters from the ground. The radius is 15 meters, and so that leaves you with the 3 meters from the ground. So if we were to graph these, now you aren't going to always have to graph these, but if you are going to graph these, you're going to go like this. Your Ferris, oh geez, this is hard to do. Your Ferris wheel is not going to be touching the ground, or going below the ground, sorry. And so we can draw our axes just along the edge. So let me try that again. So if we kind of put an axis down here, and then we go across here. So what we're going to look at is it being 3 meters from the ground with a diameter of 30. So the highest it's going to go is 33 meters. And we're going to figure out what scale we should use. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 grid lines. So we have to go up 33 in 20 grid lines. So that is, you know, kind of about 1 point something for every grid line. So the easiest way to do this is to go up by threes because then everything's going to get covered. So we're going to go 3, 6, 9, 12, 15, 18, 21, 23, sorry, 24, 27, 30, and 33 is going to be up here. I'm not going to use my whole grid, but that's okay. And then we're going to look at how to draw this. Well, it says draw the graph of one complete cycle, assuming the rider starts at the lowest point. So we've already decided the lowest point is going to be at 3 meters. Now what we want to figure out is what our x scale is going to be. It says you're going to do one complete rotation every 60 seconds. So that is going to be your period. Your period is going to be 60 seconds. So if I had to figure out where to put some key points, I would take my 60 and I would divide by 4. And I'm going to say your key points are going to happen every 15 seconds. And so we're going to go again a scale of 3. 6, 9, 12, 15, 3, 6, 9, 12, 30, 3, 6, 9, 12, 45, 3, 6, 9, 12, 60. So our first key point is down here, and then what's going to happen? Well, you're going from here, and then your next key point is going to be here when you're at the center. And so we are going to go up to 18. So at 15 seconds, you're going to go up to 18. And then at 30 seconds, you're going to go up to 33. And then at 45 seconds, you're going to go back down to 18. And then at 60 seconds, you're going to go back down to 3. And we're going to get this sinusoidal function. Okay, so now that we've got a picture of what this looks like, what we're going to try to come up with is what the equation is going to look like. So it says find the sinusoidal equation. Oh, and sorry, I could label my axes. This is time in seconds, and this is height. It's height in meters. Okay, so coming up with a sinusoidal function, like I said, the easiest one to come up with is going to be your cosine curve. So if you look at height as a function of time equal to A cos B times x minus c, and the x is a t, sorry, plus d. And we have to figure out what am I going to put in for A, what am I going to put in for B, what am I going to put in for C, and what am I going to put in for D. So we're going to do height as a function of time, and we're going to figure out what to put in for each of these. Now, amplitude. Amplitude is the distance from the center line. So if you picture a center line going right through the center of the graph, from here you go from 18 down to 3, which is 15, and you go from 18 up to 33, which is 15. So my amplitude is going to equal the radius of my Ferris wheel. And so the radius of my Ferris wheel was 15. And so we're going to go A equals 15 cos. Then we got to figure out what to put in for B. Now B is always 2 pi divided by your period. And since we know that it takes 60 seconds for one cycle, then my B value will be pi by 30. Now you will notice the textbook sometimes does not simplify, and that's fine. I just can't not. And so my B value is going to be pi by 30. Now the next part we have to figure out is what we're going to put in for our phase shift. Now because I used cosine, I don't have to do a phase shift. Cosine normally starts at the top, but instead this is starting at the bottom. So if I put a negative in front of the 15, then I don't have to do a phase shift. And I can just say pi by 30t. And then D is going to be where your center line is. So we already decided that my center line is from the bottom of here up. And so it's going to be plus 18. And that's how you come up with the equation of your sinusoidal function. Now, I always use cosine. If you wanted to do this as a sine curve, you could. It's going to have the same amplitude. It's going to have the same B value. It's going to have the same D. The only difference is that you're looking for your sine curve. You're going to look at where it's in the middle and goes up. So if you look here, this is where your graph is in the middle and then goes up. So you would say that it's a phase shift to the right 15. So I prefer to use cosine, but if you wanted to, you could use sine. So even if the question says find the sinusoidal equation, it doesn't mean you're using sine, it just means you're using a sinusoidal wave, which could be either cosine or sine. And then there'll always be a follow-up question that's going to use the equation. So this one says, what is the height of the rider at 52 seconds? So you're finding the height at 52, and then you're just plugging it in. So negative 15 cos pi divided by 30 times 52 plus 18. And you're just plugging that into your calculator. Make sure you're in radians because we've used 2 pi as our period. And so we are going to get, if we plug it in, 7.96 meters. This next question says, what is the first time that the rider's at 20 meters? So if you look here, if you look at your graph, 20 meters is here. So this would be 21. So it's like somewhere right below the 21s. Oh, I keep pushing the button. Somewhere right down here. So there's one place that they're at 21 meters. There's another one that they're at 20 meters. And then there'd be one for every single cycle, or 2 for every single cycle. So this just says what is the first time the rider's at 20 meters. And your calculator, if you plug it in, will always give you the first time. So this time you're going to put 20 in for the height equals negative 15 cos of pi by 30 t plus 18. And this time we're solving for t. So we're going to do this algebraically. We're going to first subtract 18. So you're going to get 2. Then you're going to divide by negative 15. So I'm going to get negative 2 over 15. Then to get the t by itself, you're going to do the opposite of cos. So you're going to do inverse cos, again, make sure you're in radians, of -2 divided by 15. And then you're trying to solve for t. So then you would multiply by 30 and divide by pi. And if you do that, you should get a t value of 16.3 seconds. All right, moving on. So this is again one that I would then say pause the video, and when you come back you could look to make sure that you've done it right, but I will talk it through if you need some help. So this time I'm not going to draw the graph, I'm just going to kind of think about what this is going to look like. So this is Joy's the last to board a Ferris wheel at the county fair, the loading platform. So I always start with a graph. The loading platform is 2 meters above ground level. So I'm going to put my 2 in here. The Ferris wheel has a radius of 8 and completes 1 full rotation, so has a period of 48 seconds. Determine an equation for the sinusoidal function for height in meters with respect to time. So height as a function of time equals, so I need an a value, and then I'm going to do cos, and then I need a b value of t, plus I need a d value. So to figure this out, the first thing I'm going to figure out is amplitude. Amplitude is always the radius, so it's going to be 8. My b value is always going to be 2 pi divided by p, so it's going to be pi by 24. Since they're getting on at the loading platform, so at the bottom I'm going to put the negative so I don't have to worry about any phase shifts. And then my displacement is going to be the distance of my center, which is going to be the distance from the ground plus the radius, so it's going to be plus 10. And then again, I could ask you questions following up from there about how, at what time were you this height, or at what height will you be at this time. And then lastly, just showing you that these don't always have to be modeling Ferris wheels. This is one that's doing a tide, but these could be questions about springs bouncing up and down. So you could look at when it's at the highest point, when it's at the lowest point, and then you'd have your midline, and so on and so forth. But here's a question where I'm going to give you the sinusoidal function, and I'm just going to ask you to find some information from there. So it says, by using the averages of high and low tides, the depth of water, d is a function of time, so depth is a function of time in meters, in a seaport can be approximated by the sine function, yada, 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 where t is the time in hours. What is the period of the tide? So period, we know, is 2 pi divided by b. So if I look up into my equation, I can see that my b value is all this part here. So I'm going to divide by 0.164 pi. If I plug this into my calculator, I should end up with 12.2 hours. Then it says, what is the depth of the water 2 hours into the tide cycle? So they're giving you time. So they're saying, what is the depth when the time is 2 hours? So then you're just plugging it into your calculator. 2.5 times the sine of 0.164 times pi times 2 minus 1.5, and this can all be in a big bracket, plus 13.4. And if you plug that into your calculator, you should get 14 meters. And then the last one says, what is the range of the depths of the tide? And so what we're looking at is how low and how high it can go. Well, it's kind of like asking your range. So you're going d plus a and minus a. So we said that the d value is 13.4. You can see that the a value is 2.5. So if you looked for your range of depths, it's going to go up to 15.9 and it's going to go down to 10.9. So if you looked at what the range of depths could be, it's anywhere from 10.9 to 15.9 would be the range. If you want to look at this YouTube link at the bottom, it can show you things like a spring bouncing up and down and how they've modeled using that. Good luck with Chapter 5.